Okay, so today we're talking about binary search trees. Now, in previous tutorials, I've frequently been asked the question like, what is recursion actually used for? And so this is a great example of a real use for recursion, which is actually kind of how recursion is used in the real world. So let's say that we have a set of numbers. Let's go like, no, this is bad. Not that it matters. Okay. So we have this random set of numbers here. Okay, perfect. There's no duplicates, right? Yeah, there are. Okay. And when we want to loop through them, right? Let's say I want to determine if 0 is in this set of numbers. This is a list. I have to go and check this one, this one, this one. And I'm always going to do exactly 7 operations. Okay. And now it's also possible that I'll do 1 operation, or it's possible that I'll do 12. But ultimately, when you have a lot of numbers, there's a very low probability that it will be 1 operation and a very high probability that it will be quite a high number. And so when you have lots of those, we also often want a more efficient way of doing that, of storing it. In comes the binary search tree. So how does this work? Hold on. It's gonna have to be like this. Yeah. Sorry, Excel is not the best software for this, but that's okay. What am I trying to show here? Well, good enough for now. If we need more, I'll do more. So, perfect. Great, perfect. So, what this is a tree, kind of like, right? So normally, what can we do? We can take a tree, okay, with some root element. And what do I mean by a tree, first of all? So you have some top element, okay, and then you can have a left and right node. And in a tree, by the way, each like part of the tree, so it's just like a flow chart, and each one of those little bubbles that contain some text is called a node. So then we have a left node and a right node in this case. You could normally have more, but with this type of tree, you can only have 2. And the tree, by the way, is basically a group of nodes and connected nodes, and specifically that it's kind of unidirectional. But you don't need to know those definitions. This is like in graph theory. But essentially, we have these nodes here, okay, and each one of these is a node. And each one of these can store a number, right? So, I could put 4 in here, and so on and so forth. And so the key here is that we essentially will create a certain organization where this tree is going to be defined by a certain condition. So this node is called the root node, and then these two are called children nodes, okay, where this is the left child, this is the right child. And so we could define it by the condition root is less than child. And what do I mean by that? So let's say if we have 4 here now. Now let's say we want to insert 5 into the tree. If we want to insert 5, then we'll go to the false condition, and then the left side will be true. Okay, and so I apologize for this very weird font, but whatever. So if we want to insert 5, 5 will have to go here. right? If we want to insert 3, we'll have to go here. And of course, we need an intermediate case. Well, I guess, and then 4 would also go on the right. Yeah, this is a perfectly fine condition. And we can actually do this with any data type and any sort of condition. It doesn't really matter. But I'll show that when we get into the code part. The key is, so let's say I have 5 here. So let's do this. So 4 is going to be my root node. Now when I want to add 41, I'm going to compare, is it greater than this? Then I'm going to go here. Okay. Then if I see 5, I'm going to go down the tree. So first I'm going to see that 5 is greater than 4, right? So then, since it's greater than 4, I'm going to compare it to this one. And it is in fact greater than 41. So because it's greater than 41, I'm going to go to the left. And I'm going to say 5 because it's false. Sorry, because it's less than 41. Now I'm going to go to 2. 2 is less than 4, so 2 will go here. Now I'm going to go to 11. Well, 11 is less than 41, but it's greater than, so it's less than 41, so I'm going to go left. Now it's still greater than 5, so we can put 11 here. Now we go 8. We go here, we go here, we go here. Right, it's going to be less than this, it's going to be greater than this, it's going to be less than this, so now 8 is going to go here. And so on and so forth, right? And now we'll have 1, and 1 will be less than 2, so 1 will go to the left. Oh, I skipped over 2. Not that it matters in this case. And then 8 is there, so then we're going to have, oh no, I didn't skip over 2. And then we're going to again have 0, so 0 will go here. Does it make sense to you?
Yeah, it makes sense. What's the point of doing this?
It's that, let's say I say, is 0 in the tree? Okay, if as in, is 0 in a set of numbers? Right. Okay. And I say in the list, it's 1, 2, 3, 4, 5, 6, 7 operations. Here, it's 1, 2, 3, 4. So because the data structure is storing some information about
so
saving me from looping through.
You did this comparison thing. You would be doing this comparison before you search for the number 0.
Right.
Okay. Yes, I get it.
Find 0. I'll search here. I'll do the comparison here, and it will immediately kind of, rather than just randomly looping through, it will direct me right to where I'm going.
Right. Okay. I get it.
Just give me 1 sec, Graham.
Sure.
Okay, so yeah, so now that you understand like the concept, I mean, I think that's the hardest part. What I want to point out though is what we notice is that this, if we think of these as objects, right? So this is an object, it's a node. Each node is an object. Then each node would have 3 properties, right? It would have a value, and then it would have 2 child nodes, a left node and a right node, right? Or a true node and a false node, whatever you want to call it. It doesn't really matter. I mean, it's the same thing. And I'm actually going to call them true and false, even though I think that's not traditional, right? But we can see that when it's false, it's always left, and then when it's true, it's always going to be right. And so we can basically go and define it in that way. What we'll notice is that the left node will also be a node, right? Because this is another node object. And so in that way, the tree itself is recursively defined, right? Because it is a node which has elements which are of the same type, and so on and so forth. So let's open PyCharm and actually start to implement this. So I'm going a little bit untraditionally from some of the other tutorials in the way of naming and some stuff, because I think it's a more, well, it is a more computer sciencey way of doing it, and I also think it's a bit easier to understand this way. So what I'm saying here is that we can actually represent the whole tree as just one node object, right? Because this node will store the other nodes inside of it, or so essentially, rather than having rather than naming it tree, well, it's not really a tree. It's just a node, which is storing other nodes. And so these are trees in and of itself, but they're really nodes. And so the most correct naming will be a node class. So let me show you what we're being asked here. So first of all, right, let's T9. Okay. So let's first get some things out of the way. What are the rules on for well, first of all, let me, I guess, start out with what we actually want to implement here. So the things that we're being asked to implement for this are a few things. So first of all, right, what is a BST? Well, it's just a binary tree. And yeah, I just want to point out, right, this, what are the nodes of this? There's no left and right nodes, so these are just none and none. So they can either be a node or they can be none, right? Okay. Right. So, okay, blah, blah, blah. Hold on. With right. Okay, so then there's a few things we're being asked to define a few things. Max depth, which will essentially, depth is just like, this is depth 0 or depth, might be depth 1, I'm not sure. This is depth, it doesn't matter, 2, 3, 4, etc. So we want to find the maximum depth, which we're going to do using a simple procedure known as depth first search. Then we're going to want to write an insert method to add a number into the tree, and a search function. Okay. It's basically going to determine if a certain thing is present or not. So let's define a node class directly. Okay. And so this node is going to have three properties, right? It's going to have a left, which I'm going to call true here. And this is going to be a node. What? Pretty sure you can do this. Which would be silly. And then a value. In this case, will be an integer, right? So it doesn't seem to be liking this. So let's we're just gonna not do it that way. Def init. And here, right, when we initialize it, we're gonna need to initialize it with. Actually, in this case, that's not true. With the value. Okay. And the value in this case is going to be an integer, even though it really could be a float. So let's actually change it to that. Okay. So self.value is going to be equal to value. Now, in terms of the children, it's going to be none to start with. I think right and left is probably easier, actually. What do you prefer I do? I'll do whichever you prefer. Do you have an opinion?
On whether it's left or false?
Yeah, what do you think I should do?
False.
Okay.
I think I'd be able to follow it better.
Perfect. So that's what I'll do. Okay. So we're going to initialize them to none. Why? Because to start off, right, we only have a root node and it doesn't have any children. And then we're going to add children using the insert method. So let's first just assert this for now is defined by root is greater than child. Okay, that's a condition. Now, what we can do is we can start off with an insert method. So def insert, and all we need is a value, okay, which will be a floating point. And we can immediately just say this, right? We're going to just determine which one we want to assign. So let's first create the new node. Right, which will be just value, right? And it will automatically have no children. And then we're going to say that if basically, and it's the most clean way to do it is actually without value itself. So we can say if self dot value is, hold on, it should be root is. So left, if we say left side is false, it doesn't really matter. I just want it to be clean. Greater than child will be that this way then, right? Because then false would be left side, which means that root is less than. So if self dot value is greater than dot value, then we're going to do what? Well, we can simply so this is if it's true. Yeah, if it's true, then self dot true is going to be equal to new node. Else self dot false equals new node. Make sense?
Kind of. I think I'm following.
Yeah.
Yeah, this is almost like what we did. Oh, yeah, this is what you showed on the chart for. Yeah, I think I'm following.
Sweet. Right? So that's how we're adding values, is when we decide we want to put a new value in, right? All we need to do for the current one is determine this. The key is like, I'm lying. What's the issue with what I've just done? It's that if we do this, and then we want it, like this is going to be the interface for the whole tree. And so if we want to add here, each time we're just going to be overriding this one and this one, but we don't want that. So what are we going to do? We're actually going to change this up a little bit. If self.value is greater than this, then we have two options. If self.true is none, well, then we can do this. Right? Because, no. Else, what are we going to do? Well, now, what we're going to want to do is actually insert on, well, this is where the recursion comes in. We can go to the next node, and we can call insert on that, and then it will determine if it has empty children. If it doesn't, it will call insert on its children, and so on and so forth. So we can now say that we're simply going to call self.true dot insert value. Does this make sense?
Kind of.
I know it's a bit wonky with your brain, right? Like that's how, I mean, that's the thing, right? And then we can do the same thing here. So self if So what's happening, right? Well, essentially, the key is that what we want when if you recall how I was doing this, right? Let's say I insert, once I'm inserting 4, okay? Now, what are we going to do? Well, so now I want to insert 41. Well, 41, what am I going to do? What's actually happening here? I'm going and I'm saying, insert 41. Is it greater than 4? Yes. Now, why am I putting it here? Well, because I know that there's no value here. Right. So I'm going to put 41 here. But now when we take 5, okay, I'm going to compare it here. But there is a value here. I'm not doing this. I'm not, right? What am I doing? Well, I'm actually going to go and repeat the same operation of checking here whether or not it's greater than or less than. Right. And I'm going to find out that it's less than, and that this has no child. And so because it has no child, I can put this here. But again, it would keep going down the chain as many times as necessary. Right. Which is the reason why we have it defined in this way. So we now have an insert method. Excellent. And I would be quite surprised if it didn't work. But let's say root equals node. Can say on-root.insert. And let's do this as well. And this is actually a bit of a tough one, right? But we're going to do it anyways. So we're going to say self dot. It's going to be so wonky, actually. But that's okay. You understand what I'm doing here?
No.
Okay. This is just this is a two-string method, right? And because I know that the children are both what's it called? This is where like recursion just becomes so natural eventually. And it took me a long time, so you have a node and you know that because you've defined string on the top node, that string is also going to be defined on all the inner nodes. And so what you can do, right, is just call the string function of the inner node within the string, like of the child. So this is like a recursive definition of the string, the two-string method. Okay. So I just want to quickly try this. So now let's print root. And you're going to look very ugly. Okay, excellent. So essentially, what do we have? I'll do it this way. Ooh. Left, so okay, great. So on the left is going to be 41. Then none is going to be left of 41, and 5. Excellent. So everything did store correctly. It's not a very easy to. You know what we can do? Here's a good way. So, oh shoot, didn't do this right. 1 sec. PyCharm lets us look at variables as they're stored. So let's look at how this works. So root. So first of all, we have it's defined by root is greater than child, and we know that 4 is not greater than 41, right? So this is actually the false side, and this is the true side. In our thing here. So as a result, false is storing 41 right here. You see that?
Yeah.
So then false, well, there's nothing that is greater than 41. So on the true, we have 5. Okay. And then within that, there's nothing that is greater than 5. And, oh, there's just nothing else. Oh, that's odd. Oh, because I haven't done, okay, that makes sense. When I do this, yeah. Now, we have here that's perfect. That's perfect. That's what we want. You see how this makes sense?
I think so.
So you have 4 at the top.
Right.
Then on the false condition where it's greater than 4,
41 goes to that
41.
side, yeah.
On the other side, we have 2. Then
Right,
within 41, we have 5 because 5 is less than 41.
True on the false side, you mean?
Right.
It's true. Okay, yeah. I was less than. Say, yeah.
The condition is less than, yeah.
Yeah.
So that's why.
Yep. Okay, yeah.
Perfect. So that's excellent. This is what we want. So given that, our insert method is. Let's write some other code then. Let's write a search method. This will work pretty similarly. And and this is going to be this is going to return none, of course. Now, here, what do we want? We want to return true or false, right? So it's going to return a Boolean. And essentially it's going to tell us is returns true if it's in the search tree and false if it's not, right? So what can we do? Well, it's going to be kind of similar actually, right? So on the first root node, what are we going to do? Well, let's define this is like a classic recursion. What's the base case? Well, the base case would be if in the current node, the value is going to be equal to search value. If it is, well then we can return true immediately. Otherwise, what we're going to have to do this recursively. So what can we say? Well, we need to, rather than searching the whole tree, let's just search the kind of directionally. Like this is the whole reason why we've defined the tree. And so what we can now do is say if search value is, well, let's actually, yeah, sure, I'll do it. Is, and then, well, here's this condition, right? Is greater than value. Well, then we're going to want to go to self.true. So we can call self.true.search value. Else. Oh, and we're going to return it as well. Does that make sense? And that's all we need, actually. Does this make sense to you?
Sort of. I'm just having trouble distracting around it, but.
Well, okay. So, what do we want to do here? Same process, right? So we start with 4, and we can immediately say, and let's say we're searching for the number 4. Well, then the first time we'll immediately have this first condition. This, if the current value, the value of the current node, right, is equal to the search value, then we immediately know it's true, right?
Right.
Right. So that's how we're doing that. So let's change this value. Now let's say we're looking for 5. Well, what can we do? We can go and evaluate the condition. So we can say on this one, if 4 is greater than, like, as we're basically saying, where would the search key have been sorted to? So what do I mean by that? Well, we can say, is 5 greater than 4? No. Yes, sorry. Sorry, is 5 less than 4? No. And so it's going to go to the right. We know that 5 would be on the right-hand side. We can so what we can do is we can now take this as a node and make this the root node in our search. For just like classical recursion. So now we're going to do the same thing. We're going to say, is 41 5? No. So now we need to keep searching deeper. You understand? So we can say now, okay, well, 41, what about 41? Well, it is less than 41. And so we can go here. And sure enough, we found 5. We return true all the way back. Now, the other key is that we actually need to have an extra condition here, which is if self.true is none. Because we can immediately stop searching because we know where it would have been sorted and we know that, well, it isn't there. Okay, so this makes sense to you now.
Yes.
Great. Let's refactor a little bit. Let's just clean some things up. So first things first, rather than duplicating all this code in both of these places, and it is perfect, completely duplicated code, what can we do? Well, let's define a condition here. Let's just say relevant child, right, is equal to self.true if self.value is greater than value, else self.false. Make sense? And then what we can do is in all of these places, we can just do relevant child. And delete this.
Whoa.
Does that make sense?
Kind of, I guess. I don't know.
Ooh, that's an interesting. Yeah, it should work. Actually, this doesn't work. I'll just leave it. I mean, it might work. I'm not 100% sure, so I'm just going to leave it the way it was. There's one more thing to consider here. Let's use some dynamic programming. Let's general. I'll do this in a second. I'll do this. Let's first define our last function, which is this depth max depth. And so what do I mean by depth? Well, we've gone over this, right? So this is 1, this is 2, this is 3. So basically, how many layers of recursion there are at the deepest point of the tree. So how can we do this? Well, first we want to say if self.child or an. So let's actually, it's easier for us to define the recursive case first here. So what's a recursive case? Well, the max depth of, 4 is going to be the max depth of this plus 1, like the depth of this plus 1, right? Similarly, this is going to be the max depth, right? You know what I'm saying. So essentially what we can do is we can say return 1 plus max depth of the children. And specifically, what is it going to be? Well, it could either be the depth of this, or it could be the depth of this, whichever depth is deeper, right?
So long as yeah.
Right, like if this one is deeper and there's a 7 here and a 9 here, well, then it's going to be this.
Yeah.
Right.
Yeah.
So what we can now say actually is we're going to say the maximum of self.left and oops, I'm doing this wrong. And self.right. Max. Sorry. Yes? Yeah.
Yeah. Wait,
now,
I was just looking at the wrong thing. Yeah.
And in the base case, well, what is it? Really, it's just that is there actually a left or a right? So if there's no left or right, then what? Well, we can say this.
Wait, so there's no left or if there was no left or right, wouldn't it just be one value?
Right. You could yeah, exactly. Oh, actually, it would be 0. No, it'd be 1. You're right. No, it'd be 0. It'd be 0. But I'll show you in a second what I mean. We should do it like this. So if self dot false is not none, and self dot true is not none, then we can do this. So we'll say our children, child depth, we'll call it, is equal to this. Otherwise, there's no children, right? So it's just going to be equal to 0. And so we can just put plus child depth. And that way, if this has no children, then the depth will just be 1. And if this has no children, the depth will just be 1. And that way will be 1 plus 1, and it'll be 2. There's one issue here that remains. And that is the issue that if one of these is true, so if self.true exists, but self.false doesn't exist, well, we still should actually proceed and search self.true. So probably the easiest way to do this is to say, if self.false is not none, and there are probably cleaner ways of doing this, then do child depth, else, if, well, then if and here, all we're going to do is we're going to remove the max. I'm going to do this. Does this make sense to you?
Yeah, I'm just trying to follow along because it was I just switched a couple times.
Oh, you're following along on your computer.
Yeah, I am following. Yeah. Because I had the whole thing down, and then you switched it. Now I'm just kind of just...
Got him.
Yeah. Where was it? Yeah, I'd probably say recursion and classes are probably my two.
Recursion is tough. Recursion is tough, man.
Yeah, I still think I'm having problems with recursion, but I think I need to do some review.
Yeah. So, but essentially the idea here is, if we think about this, if there's a child element for false, or the other way, actually, the most correct way of doing this is instance, and then we could say, but I'm not going to do it this way. So basically, if self.false is a node, well then, let's set some variable equal to the max depth of that, right?
Right.
Then let's do the same for self.true, and if the depth of false is greater than the depth of true, then use the depth of false. If the depth of true is greater, use the depth of true. Then return 1 plus the child depth. Now, if there are no children, because this is none and this is none, well, child depth here is already defined as 0, and so we'll have 1 plus 0, which will give us 1. Which, like, this has a depth of 1, which is the expected result. Right.
Right.
So that's great. So let's try it out. So first of all, let's recreate this tree a little bit. So actually, the tree that we have here, we want to figure out a few things. So let's first print root.search for 1, and we should find it's false. Then let's see print root.search, and let's see print root.search 2. So as I'm sure you would agree, we should see false, true, true.
Right.
Great. Whoa. Crazy. So we made a mistake.
Dang.
I will go to that in a second. The other thing I want to test is print root.maxDepth. And so for something like this, it should be 1, 2, 3, right?
Right. Oh,
so max depth is working properly. But our search function is a little broken. David made a boo-boo. Okay. Oh. So this looks right. If it's greater, oh. Oh. See what I did there?
Search value is greater than search value.
Yeah. That'll do it.
That it?
There we go. False, true, true. So that's working. Now I do want to add a little bit of a dynamic programming spin to this. Let's do something better. Let's make this able. What I'm trying to show here, that technically these can actually store any data type with any condition. How? So what we can do now, let's remove the restriction on floating point, even though I'll leave it for now actually. And now let's say self.condition is going to be equal to some given condition. Right?
Right.
And this is a function. So actually, Python likes to call callables. Self.condition is now going to be equal to condition. And so what is condition? Condition is going to be like some function that takes A and B and returns true or false. Right? Well, in this case, it'll be return A is greater than B. Make sense? Like, you agree this is what that does?
Right, yeah.
So what I want to be able to do now is say this, root greater than, and this is going to get passed as a variable. And now, why am I doing this? Well, because what I intend here is to, instead of have this condition here, to instead say if self.condition AB. So if it's true,
yeah,
and instead of AB, we're going to have here self.value and value, then go do those things. And I just need to refactor this so that condition equals to self.condition. I have to copy the function in this case. Here we need it, and that should be all. Yeah, and let's replace this in all of these places now. So if self.value is, so then again, we're going to say if self.condition and that should actually be all of the places. So first things first, let's actually verify that it operates identically, right? You would agree. And so it does. And so this is great because what this means now is we could actually store anything, right? Here's a good example. And now.
Oh, longer string. That sounds like a test question or something. Or like an assignment question.
Right, and then we would now have return len A is greater than len B, right? And you would agree that this will also do a similar sort of thing. So now let's completely change this up. Let's remove the value of float, because the value can actually be any. And I'll actually make you in. So why not? Because really, there's no reason for us to restrict it. Why would we? Anything with an equal sign, like anything that can be compared, basically, is fair game. Should be. So now let's do longer string. You'll notice no calling it here. You just want, if you call it, it will cause an error actually, but there's no value. You just want to pass that function as a variable, and so we have that, and so what we can do is say insert. Now we're going to have insert for 41. Let's do an empty string, or let's do 5, and let's do 255, and then let's do root.insert an empty string. Yeah?
Yeah.
And now, oh, I did do one thing wrong. We actually do need a condition here, which is that if a value already exists in the tree, it shouldn't be added again. So let's just do it. It actually, it's cheaper to do this as you go, but I'm too lazy to do that. So instead, I will just say if self.search for a value, then just return. And now we'll do that. You agree? Because if the value's in there, then it will just not insert it. Right?
Right. Okay,
sweet. So now, let's do this. It's actually quite an inefficient implementation, but I don't care. That's fine. So what we can do is test it. So let's now do the same thing. Let's search for 4 and for 41 and for empty string. We should find it with this algorithm. We're finding all of these things. But now if we do space, we'll get false. And so it seems to be looking now for any type with any condition. And you could do the same for objects. And that's why this is a powerful structure, is because really it's just defining it based on an arbitrary condition. And this is the power of dynamic programming as well, that this same class, right, you could import it and you could use it for any structure you wanted to, right?
Right.
You know what I mean?
Like for length, yeah.
Yeah, or for any other property, right? Like it could be based on like some fancy, really long computational function or biological function. Like, you know what I mean?
Right.
Like this function is arbitrary. The only restriction on this function is that it takes up 2 parameters A and B and returns a Boolean object.
Okay.
Heck, it could even be based on the type. What?
Right. Will you be posting this like after the lecture? Just so I didn't finish. I stopped following after the dynamic programming part.
Yeah, I'll post it. Sure.
Oh, okay, cool. Thank you. Okay.
Yeah. And then of course we use a lambda function here as well to say the same. And this is why this is so powerful, because you can do all of this kinds of stuff kind of out of the blue. So, I mean, that's really all for today. Do you have any questions about this or about what's it called? About well, really about anything?
I have a question about one of the assignment questions, but
go for it.
Okay, so for assignment 9, question 2, I'm just kind of like the stocks one.
Okay.
I did it and I got like the trades, like it's supposed to be like the high one, the high and the low. I think like that's what I'm imagining is like the highest value in the CSV file, and the lowest value in the CSV file because you want to trade the lowest and sell at the highest.
Yeah.
Is that all we have to do? Because I'm just want to make sure, because I know I can't ask you what the hidden test cases are, but like I'm trying to think of other ways that they would test us on a test case like this, because there's all like would you have like another file or something that you would test it on, or like
Yeah.
I'm not sure how to make my like my code or my block more robust to like what you will throw at it when it gets marked.
Yeah, wait, let me look at the test cases.
Okay.
Yeah, you know what? I don't see any test cases that are especially out there. They seem to be quite standard test cases, actually.
Okay.
I wouldn't worry too much. I mean, if you want, I could take a look at your function, but I wouldn't worry too much.
Okay. All right. I don't know if I have any. And for like, so when I was even like when I started, I could do like, I understand like the CSV because it's pretty much, it's a lot of like the starting code in the CSV seems as if it's very like obviously very similar to what we did in class, but then everything after that, it's like depending on if it's CSV or a JSON file or whatever, it's all dependent on like how it's all based on like previous learning of like dictionaries and lists and stuff like that, right?
Yeah, absolutely.
Okay. Yeah, because that's why even for question 1, I struggled because like the JSON file is like a dictionary, and then in the dictionaries there's the key, and the key leads to a list, and then the list leads to a whole bunch of dictionaries with a whole bunch of keys. And I don't know, it took me a while to like wrap my head around the concept of I guess like how to access it, because it's a little bit more difficult than like a nested dictionary or something like that.
You know, it's funny because that's real programming. That's this is what I'm working on right now. Okay, and this is all dictionaries, and like here's another one, and like look at this craziness. I mean, I know you can't see details, but like these are all different indentation layers, and I have like 120,000 lines of data in that format. So, you know, on one hand, it is certainly like it takes a lot to get your head around, but it's also something like it's the most important thing, because you know, really that's what ends up happening in programming is you end up with these very complex dictionaries and data structures, because you know, in the real world, like all it is just working with data basically.
Right.
And so like my program is, you know, nothing out there. It's like just doing some analysis on, like it's like a genome sequencing and analysis program. And so it's not like it's some fancy complicated app or anything, and yet, you know, really all I'm ending up doing is working with a ton of data. So yeah, the short answer is yeah, you just have to get good with dictionaries.
Yeah. Yeah, I'm just really worried for the exam. Because I realized after the midterm, it's 2 weeks, like, well, 2 weeks pretty much, well, 3 weeks with that extra week for the exam. And the midterm took me a really long time, and I'm worried about how long the exam is going to take me. But I'm like, how do I know we have the week like after this week where we don't have any assignments.
Right.
What would you recommend that I do during that week? Just like leak code or something like that, or
Sleep.
I think I need some practice because my classes ability, although is I mean like my classes, like my understanding of classes is not like I don't know. It took me a while, and I still feel like there's some gaps. But I got the assignments done. That took quite a while.
Yeah, I mean, it's leak code is a big one. Leak code is great, but I don't know how good it will get you at classes. What you can do is redo the classes one. Honestly, if you're good at these, if you can do these assignments well, I wouldn't worry about the exam. You know, it'll take you some of the day. It took me, when I wrote that exam, it took me a few hours as well. Like, it took me probably 4 or 5.
My midterm took me the whole day. I started at 9:30 and I probably ended at like 11. And it wasn't because I was like taking my time. It was because I was like legitimately trying to figure out the question.
Yeah. So, yeah, I
But,
mean, that's
like,
not uncommon. I mean,
it is what it is.
it's not uncommon. I would say I wouldn't worry about that too much. The exam is not much harder than the midterm. Like, it includes more content, obviously, because, you know, the midterm is half the
like
course,
real
the
depth
exam
and
is
stuff.
at the end. But in terms of actual difficulty, it's not harder.
Oh, I thought whenever it gets mentioned in class or like, I don't know, from wherever, it's like the exams can be way harder than the midterm was.
In content, yeah.
Oh, because you mean like based on like like what we learned. Oh, I thought it was gonna be like the questions are gonna be a lot more difficult.
No, and you know what? This time it was a harder midterm too, I think. Especially people found the last question, which ironically is the question I wrote, particularly challenging.
Right.
But kind of feel bad about that. But also it was a good question, so I'm, you know, like,
Yeah, took me, actually that wasn't even the one that took me the longest. It was the bananagrams question, I think, that took me the longest.
yeah.
And it's always like one thing for whenever I do it. Like I'm trying to like there's one thing, like I just need to add like a built-in method or something, and that's the difference between me getting all the test cases wrong and getting them right.
I know what you mean. Yeah, look, I think practice. That's really all you can do. I mean, oh, did I just do something bad with my power supply? Yeah, practice. I wouldn't stress too much. Like,
Okay.
we say it's harder. The truth is, you have been working. Like, I can tell that you worked quite hard throughout the course. I'm not worried. I'm genuinely not worried for you. Like, there are students in the course who I'm acutely aware of who are like struggling for various reasons, usually because they either like get discouraged by the midterm, or the most common thing with this course is people think that the course is easy until the midterm comes, and then they get a 50 on the midterm, or usually even worse than that actually, and then they're like, oh crap, I actually need to work hard to do well in this course.
Yeah. Jeez.
And those are the people where it's like, you know, I'm worried about their performance in the midterm. For that, and that's why we say it's harder. It's like harder as in, you know, if you thought the midterm was like, oh my god, I can't do it, then you might have an issue on the, and you don't work hard to fix that, then you'll have a problem on the exam. Yeah, but if you did the midterm, did okay on the midterm, you know, even if it took you 8 hours, you know, that's not uncommon. I got to be honest, that's not so uncommon. But ultimately, you're in a good place.
Hopefully.
Oh,
Like I think. Yeah.
Did I really hope you do well in this course? Like, honestly, I mean,
Yeah, so do I. So do I.
Yeah, no, but the different, like, when people put in the work in this course, especially, like, I definitely like to see people succeed.
Yeah, I think I need to practice my classes and all. Like I just don't understand. I think I'm having trouble understanding like all the I don't know. I have to go over it again.
I would
Just
go back
after
to dictionaries.
lectures.
Go
Pardon?
back to dictionaries. Get good with those. Once you
Yeah.
understand dictionaries, classes are a little bit easier. Then come back to classes.
Okay. I think I'm pretty good with dictionaries, but maybe I'll have to go over it again. I just thought it's not like the like I think it's more like the concept, like the because I know for the exam, especially after the exam, like I figured out, like it doesn't it's more of the understanding of how things work. rather than just being able to like spit it out from the midterms. So I think I had lacked understanding of how like behind like how like the Python tutor, like how you can watch it go through. I think that was my biggest issue. But yeah, I don't know. I have to
Take
see
some
that.
time. If you're still having trouble with classes, send me an email. I will take you through, and I think I have a pretty good way of explaining classes and helping with that. So if you're having trouble, like tomorrow or I'm not free on Thursday, but any other time I'm good to help you. So just
Okay.
message me, or email me or whatever, and we can get on a call and go over it.
Okay, that'd be great. Thank you.
Okay.
All right.
Okay.
Thank you.
No
All right.
problem. So on that note, I will stop recording.